Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 4.1 on exponential functions. To begin, we're going to actually answer the question, what is an exponential function? And the short answer is, an exponential function is a function of the form f of x is equal to b to the x power. And now they can certainly be a lot more complicated than this, but in general, this b will be a constant greater than 0 and not equal to 1. We'll talk about why that is in a second. But the key feature of an exponential function is that you've got your independent variable in the exponent. So, for example, if you've got something like y is equal to 2 raised to the x power, this would be an example of an exponential function. On the other hand, if you had something like x squared, this function has an exponent, but it's not an exponential function because the variable is not in the exponent. In fact, we know that this is a quadratic function because it is a second-degree polynomial. Now, the letter b has a name as well. We call that the base of the exponential function, and the value of the base has a pretty significant impact on the shape of the graph, and we'll talk about the graph a little bit later on in the section. There are some restrictions on the base, however, in order for this thing to be able to function in an interesting or reasonable manner. And the first is that the base has to be a positive number. And the reason for that is, think about if we had a negative base. So let's say we had negative 2 to the x power. Well, if you plug in a positive number for x, say 2, we would have negative 2 squared, which would be positive 4. Let's say you plug in an odd number for x, like 3, negative 2 cubed would actually be negative 8. So sometimes you get positive outputs if you plug in even exponents. You'll get negative outputs if you plug in odd exponents. But it even gets worse than that, because there's no rule saying that the thing you plug in for x has to be an integer. We could take this negative 2, if it actually worked as a function, and raise it to the 1/2 power. But we know the 1/2 power is the same as the square root. So this wouldn't even give you a real number output. It wouldn't be in the domain of the function. And so a negative base just causes all kinds of complications. It would actually be impossible to graph. It doesn't work. And so we say bases have to be positive numbers, strictly greater than 0. And we also set the additional restriction that they can't be equal to 1. And the reason is that also creates a different kind of uninteresting when we graph. Because if you have 1 raised to the x power, no matter what you plug in for x, you would always just get out 1. So that would actually just be a horizontal line and not an actual exponential function. All right, so remember these two restrictions for the base. They will come back up once we start talking about logarithmic functions in section 4.2. Base has to be positive, can't be equal to 1. Example 1 in this section is pretty straightforward. This is just a little bit of function evaluation, which we first covered back in section 2.1, mixed now with exponential functions. So try pausing the video and see if you can find the answers to example 1. All right, so for part A, we've got g of 1. So we're going to plug in 1 for x into the g function, which would give us 2 to the 1 minus 1 power, all right, because the 1 goes in for this x right here. And we can do the math inside the exponent now. 1 minus 1 is, of course, 0. So this is 2 to the 0th power. And remember, by properties of exponents, anything raised to the 0th power is always equal to 1. And so g of 1 would be equal to 1. Part B gets a little bit more complicated. We've got h of 3/2. So we're going to plug 3/2 in for x into the h function. So this is going to be 1/4 to the 3/2 power. And so remember what a fractional exponent tells you to do. The denominator of the exponent tells you what root to take, and the numerator of the exponent is just a traditional exponent. You raise it to that numerator power. So we need to take a square root, and we need to cube the number. Again, the order doesn't matter. You could cube first and then root, or take the root and then cube, but if the root works out nicely, it's usually best to go for that first just to bring the number down to a smaller state. And so in this case it does. I'm going to take the square root of 1/4, and then I'm going to cube it. So, properties of square roots, which are just inherited from properties of exponents. To take the square root of fraction, you just take the square root of both the top and bottom, which in this case would be 1/2. And now this is cubed. And two ways to think about this. You could write out 1/2 3 times and multiply it out. Or the same property that we just used for the root. If you want to cube a fraction, you cube the top, you cube the bottom. Which either way is going to give us 1/8 in this case. All right, so really just a review of exponents, more so than anything else, because we are going to be using exponents a lot, of course, in the exponential function section. And then last but not least, in part C, we've got f of -2. So we're going to plug -2 in for x. This would give us 3 to the -2nd power. Another property of exponents. 3 to the -2nd would be the same as 1/3 squared, or 1/9. Now let's take a look at a graph of an exponential function. We're asked to sketch the graph of the function 2 to the x power. And for this problem and the next one, we're going to go back to the section 2.2 method of graphing by just picking the right ordered pairs. And we're just going to pick a handful of x values centered around 0. So we'll do 0, 1, 2, but also a little bit to the left. We'll do -1 and -2 as well. And this should give us a pretty good picture of what's going on. Of course, as always, to find the y values, we're just going to take our x's and plug them back into the function. So let's start with 0. If we evaluated f of 0, so we plug 0 in for x. Again, property of exponents, anything raised to the 0th power is always 1. If you plug in 1 for x, we would have 2 to the 1st power, which would just be 2. And if we plugged in 2 for x, we would have 2 squared, which would be 4. If you were to keep going, you would find it doubles every time. So if you plugged in 3, that would be 2 to the 8th, or 2 cubed, which would be 8. 2 to the 4th would be 16, so on and so forth. So every time x increases by 1, the y value doubles. This is sometimes called the doubling function because of this behavior. For negative exponents, so let's say we evaluate f of -1. Again, property of exponents, 2 to the -1st power would be the same as 1/2 to the 1st power, or 1/2. And similarly, 2 to the -2nd would be 1/2 squared, or 1/4. So if you were to keep going in the negative direction, the denominator would double every time. So we would get 1/8, 1/16, 1/32, so on and so forth. All right, so let's plot these ordered pairs and see what shape we're getting from the graph. All right, so we got 0, 1. It's our y-intercept. We've got 1, 2. And then we've got 2, 4. If we were to go over to 3, it would be off the chart at this point. It would be up at 8. So this thing gets very steep very quickly. At -1, we have a y value of 1/2. And at -2, we have a y value of 1/4. So the y values are getting closer and closer to 0 as we go to the left. And so the shape we get out of the graph looks something like this. So as we go to the right, the graph is going to get steeper and steeper. And as we go to the left, the graph is going to get closer and closer to 0. So it is leveling off towards the x-axis, but it never quite reaches it. It just gets infinitely close as we go. Because of this, we call the x-axis, this horizontal line that it approaches, a horizontal asymptote. From looking at the graph, we can also pick out a couple of other important features. The domain of the function. This graph goes forever to the left and forever to the right. The domain is from -infinity to +infinity, which makes sense because no matter what real number you plug in for x here, 2 to the x power is still a real number. And the range of this function, the y values, go forever up to +infinity, but they never go below 0. In fact, they never even reach 0. This line gets closer and closer to a y value of 0, but it never touches it. And so the range would be from 0 not included, so with parentheses this time around, to +infinity. As we read this graph from left to right, the y values are always getting bigger. This is a function that is always increasing from left to right. And because of that, this behavior, this shape, we call exponential growth. Exponential functions are actually really useful for modeling real-world phenomenon, with exponential growth being applied very frequently to anything related to populations. So populations grow exponentially because the higher a population, the faster it will grow. But also anything related to population size, like government spending, Medicare expenditures, things of that nature, also grow exponentially. So those can be modeled with exponential functions as well. Another thing that's really commonly modeled with exponential growth is interest, the amount of interest that builds up on investments. That also grows exponentially because the more money you have invested, the more interest that builds up. And so you get one of these shapes where the bigger your x value gets, the steeper the growth gets. Let's take a look at one more. And this one is going to look a little bit different once we finish graphing it. This time we're asked to sketch the graph of 1/5 to the x power. And the process that we're going to use for this one is the same. We're going to pick the exact same x values just to figure out the pattern. So -2 to +2. All right, and just like before, we plug the x's back in. If we plug in 0, 1/5 to the 0 is still 1. Anything to the 0th is 1. If we plug in 1 for x, we get 1/5 to the first power, which is just 1/5 itself. And if we plug in 2 for x, we get 1/5 squared, which would be 1/25. For negative exponents, remember the property from early on in chapter P. If you have a fraction raised to a negative exponent, you can flip the entire fraction to turn the exponent positive. So if we had 1/5 to the negative first power, this would be the same as 5 to the first power, or 5. And similarly, 1/5 to the negative second would be the same as just 5 squared, or 25. And so if we plot our ordered pairs, we've got 0, 1. This time as we go to the right, though, it's getting closer to 0. So at 1, we've got 1/5, 0.2. And at 2, we've got 1/25. So it's already getting really close to 0. 3 would be 1/125th, 1 over 5 cubed. At -1, we're up at 5. And at -2, we would be up at 25 off the chart. And so we get a shape that's actually a lot like the one we had on the previous slide, but flipped. So we get something that looks like this. So this time, it's leveling off to 0 as you go to the right, but it's still leveling off to the x-axis, so this is still a horizontal asymptote. Still a horizontal line that the graph levels off to. The domain, it's still forever to the left, forever to the right. Negative infinity to positive infinity. In fact, that will always be the domain of an exponential function. And the range, the y values, is still 0 not included to positive infinity. This time around, however, as we read the graph from left to right, the function is decreasing. The y values are getting smaller. So this is not called exponential growth anymore. This shape is now called exponential decay. And a lot of people, when they think of exponential decay, think of it the wrong way, because they think of it as just the true reverse of exponential growth. So exponential growth is growth that starts off kind of slow and speeds up over time. So when people hear exponential decay, they think the same thing. Decay that starts off kind of slow and then speeds up over time. But that's not the shape we have here. Exponential decay is decay decreasing that starts off fast and levels off over time. The decay slows down over time. Some examples in the real world of exponential decay, probably the most famous is radioactive isotopes decay exponentially. The more of a radioactive isotope you have, the faster it breaks down. It's due to a concept called half-life, where at set time intervals, the radioactive substance always cuts itself in half. This is how we do things like carbon dating. Another example of exponential decay could be, let's say, the value of a brand new car after you drive it off of a car lot. Right? As soon as you buy that car and you drive it away, the value of the car is going to decrease pretty sharply. And over the first couple of years, and this also depends on mileage, of course, the value will continue to drop pretty steeply. But then over time, the value kind of levels out and year by year starts to decay less and less. All right, and this is not taking into account anything special like a collector edition, some kind of car whose value would eventually go back up after it reaches a certain age. Well, we've seen examples of two specific exponential function graphs so far, but what about the others? And it turns out that all exponential functions will either fit one of these two shapes, exponential growth or exponential decay. So let's think about when that would happen. Well, previously we graphed 2 to the x. And so when we were graphing our x and our y values, and let's just do -1, 0, and 1 here, we got 1/2, 1, 2. Well, if you were graphing 5 to the x, you would get 1/5, 1, 5. So in other words, it would have grown a little bit steeper to the right, and it would have flattened out a little bit faster to the left, but it would have been the same basic shape. If you had graphed 7 to the x, you would get 1/7, 1, 7. So same idea, even a little bit steeper to the right and a little bit flatter to the left, but same basic shape. And it turns out you will get exponential growth if you are graphing b to the x power anytime your base is greater than 1. So 2 to the x, 5 to the x, 7 to the x, 10 to the x would all have this same basic shape of exponential growth. We got exponential decay when we graphed 1/5 to the x. Or another way you could think about that, if you wrote it as a decimal, it would have been 0.2 to the x. And it turns out you will get exponential decay anytime your base is between 0 and 1. So 1/2 to the x would give you a similar shape. 1/5 to the x, 1/10 to the x would all give you exponential decay. Now, these are the only two options. Either your base is greater than 1 or it's between 0 and 1. And the reason for that is because the restrictions we set on the base back when we defined the function on the first slide. The base is always a positive number and it's never equal to 1. So it has to fall into one of these two cases. That said, there is another way that exponential decay is sometimes modeled with a base greater than 1, and that's by using a negative exponent instead. And that's because of properties of exponents. 2 to the negative x would be the same graph as 1/2 to the positive x. So it would fit the same exponential decay shape that we got with 1/5 to the x. So it's just kind of two different ways of accomplishing the same thing. Negative exponents will basically flip this behavior on its head. The last type of problem we're going to see in this section is solving certain types of exponential equations. We'll go into more detail on those in section 4.4. In order to solve the basic exponential equations we're going to see in this section, we're going to use something called the one-to-one property of exponential functions, which says that if you have b to the x1 equal to b to the x2, in other words, both sides are a power of the same base, then the only way these two things can be equal to each other is if the exponents are the same. Right, this makes sense if you think about it. 2 squared would be equal to 2 squared. That's the same thing on both sides of the equal sign. But 2 to the 0th power would not be the same as 2 squared, right? Because 2 to the 0th would be 1 and 2 squared would be 4. So if the base is the same on both sides, the only way the two sides of the equation can be equal is if the exponents are the same. And so this is how we're going to solve the equations. Our goal will be to write both sides of the equal sign as a power of the same base, and then set the exponents equal. So let's take a look at some examples. And for the most part, the exponential equations we're going to look at in this section are pretty basic. So a lot of them you might be able to just look at and determine the answer without really doing a lot of scratch work. But let's reason our way through it with the one-to-one property as mainly prep work for section 4.4, when the equations are going to get a little bit more complicated. So starting with part A, we're asked to solve the equation 5 to the x power is equal to 25. So our goal then would be to write both sides as a power of the same base. Well, in this case, it would be pretty easy since we can write 25 as 5 squared. And since the base is the same on both sides, by the one-to-one property, we can set the exponents equal to each other. And then if they were more complicated exponents, we would solve for x. But since this is already solved for x, we're just done. X has to be equal to 2. In part B, we've got 5 to the x power is equal to 1. So same idea, but this relies again on property of exponents. We can still write both sides as a power of base 5 by writing 1 as 5 to the 0th power. And so the question is, what exponent x would make this equal to 1? The answer is 0. X has to be equal to 0. In part C, we've got 2 to the x is equal to 1/8. So this one's going to require an extra step, because although 8 is 2 cubed, this is not quite right. This is not just b to the x1 is equal to b to the x2. So the one-to-one property doesn't apply yet. Well, fortunately, we can make use of exponents. Normally, if we have a negative exponent, we bring it down into the denominator to make it positive. But you can also use this property in reverse. So 1 over 2 cubed would be the same as 2 to the negative 3rd power. And so in this case, the power of 2 that would give you 1/8, by setting the exponents equal to each other, we get x is equal to -3. In part D, we apply one more property of exponents to add an extra layer to the problem. So we've got 2/3 to the x power is equal to 9/4. So our goal is to eventually get 2/3 if we can on the right-hand side. Well, 9 would be 3 squared, and 4 would be 2 squared. Well, recall from properties of exponents that if you have a fraction raised to a power, you just raise the numerator and denominator to that power. So if we use this property in reverse, 3 squared over 9 squared, 9/4, would have to be 3/2 squared. Right? And it's entirely possible that you could skip this middle step and go straight to recognizing the fact that 9/4 is 3/2 squared. That's also fine. But that's still not quite right, because 3/2 and 2/3 are reciprocals of each other. So again, we use that property of negative exponents. That if you change the sign of the exponent, it flips the fraction. So 3/2 squared would be the same as 2/3 to the -2nd. So now we have the same base on both sides, which means x would have to be equal to -2. In part E, we see our first problem with an exponent other than just x, which for the most part doesn't change the problem until you get to the final step. So we've got 10 to the 2x is equal to 10,000, or 1,000. So a quick review of positive powers of 10. So 10 to the first power would of course be 10. 10 squared, or 10 times 10, would be 100. 10 cubed, you would multiply by 10 again and get 1,000. So basically, if you have a 1 followed by a bunch of zeros, you can just count the number of zeros you have, and that will give you the power of 10 that you're working with. All right, so in this case, we have 10 to the 2x is equal to 10 cubed. And so now that both sides are written as a power of the same thing, 10, we set the exponents equal to each other. So 2x would have to be equal to 3. And then last but not least, this time around, we have to solve for x after we set the exponents equal. So we would just divide both sides of this equation by 2. And so the exponent that would make this true would be 3/2, or 1.5. Example 5 is similar to example 4. It's just now also mixing in a little bit of function notation. So in this case, we're told that g of x is equal to 1/3 to the x power, and h of x is equal to 10 to the x. So in part A, we're asked to solve for x if g of x is equal to 1/9. So in other words, if 1/3 to the x is equal to 1/9. And since 1/9 is 1/3 squared, that means x would have to be equal to 2. Same thing for h to the x, but now we're going to do a quick review of negative powers of 10. So 10 to the negative first power would be 1/10, 1 over 10, or 0.1. 10 to the negative second would be 1 over 10 squared, 1 over 100, 0.01. So in other words, if you have just a decimal with a bunch of zeros to a 1, you imagine the decimal starting to the right of the 1, and then you count how many places to the left that it goes to get the exponent. 1, 2, to get 10 to the negative second. So in this case, this would be 1, 2, 3, 4 places to the left of the 1. So h of x, which is 10 to the x, would have to be equal to 10 to the negative fourth power. Or in other words, x would be equal to negative 4. The last topic in this section is regarding a specific base to an exponential function, and this is called the natural base, which is represented with the letter e. And this shows up extremely frequently in mathematics. We're not going to run into it a whole lot here in Math 101, but this number is very common, primarily because it has some very useful properties in calculus that keeps it around. But it tends to pop up in all kind of applications, and we will be referencing a lot once we get to logarithms in section 4.2. So the first thing that's important to recognize is that e is just a fixed number, kind of like pi. E is about 2.71828, or usually just think of it as being about 2.72. Just like we remember that pi is about 3.14. In other words, if you're dealing with an exponential function e to the x power, this is approximately equal to 2.72 to the x power. And so that means, what shape would you get if you tried to graph e to the x? Well, earlier, when we were talking about exponential growth and exponential decay, we said that we end up with exponential growth anytime the base is greater than 1. And e is bigger than 1, it's 2.72. So if you were to graph e to the x, you would get a graph of exponential growth. All right, so the main takeaway here is that e is just a number. It's just a number that we represent with a letter. So if you see it in a problem, don't let it scare you. It doesn't change things that much. So now let's work a couple of quick examples with base e. So we're going to let the function m of x be e to the x. And in part A, we're asked to approximate m of 2, rounding to 2 decimal places. So this is just function evaluation. M of 2, we're going to plug in 2 for x. So this would be e squared. And we want to approximate this to 2 decimal places. Now, scientific calculators have an e button on them. So you'll want to make sure you look for that because it comes in handy. And you just want to type into your calculator e squared. And so if you typed in e squared, you would get a number that is about, rounded up, 7.39. And then in part B, we're asked to solve for x if m of x is equal to 1/3. And since m of x is e to the x, we have e to the x is equal to 1 over e cubed, which by property of exponents would be e to the negative third. And so, by the one-to-one property of exponential functions, we can set the exponents equal to each other, meaning x would have to be equal to negative 3. And that is it for section 4.1. A somewhat shorter section, relatively speaking, for the types of problems you can expect from this section. You should be able to evaluate exponential functions and sketch basic graphs. And for the sketching of the graphs, in this section, we just pick a handful of x values around 0 in order to get a good picture. And then you should be able to solve exponential equations using the one-to-one property. But truth be told, we will be doing this in more detail in section 4.4, where the equations will start to get a little bit more complicated. So that's going to show back up a little bit later on. And problem number 3 is just an extension of that, where we mix function notation. So with that said, as always, if you guys have any questions, please make sure you let me know, and I will see you in the next video.